Hello everyone, welcome to this week's Crunch seminar. Today we have two speakers. The first talk is by Dr. Jingjing Zhang, who will present her work on PINNs for challenging multiphase flow problems in subsurface energy systems, gravity-induced dual shocks, interface solubility, and stratified CO2 migration. Jingjing Zhang is a PhD graduate in petroleum engineering from Texas A&M University and will soon join Chongqing University of Science and Technology as a faculty member. Under the joint supervision of Dr. Eduardo Geldin from the Department of Petroleum Engineering and Dr. Ulysses Braga Neto from the Department of Electrical and Computer Engineering, her research applies physics-informed neural networks to challenging multi-phase flow problems involving complex rock and fluid properties. She has developed machine learning frameworks for simulating gravity-driven water flooding and carbon dioxide migration in layered saline aquifers, which are critical to enhanced hydrocarbon recovery and geological carbon sequestration. Combining her engineering background with industry experience at Kinder Morgan, Chevron, and ExxonMobil, she aims to advance scientific machine learning for more accurate subsurface modeling and cleaner, more efficient energy development. With this brief introduction, I invite Jingjing to present her work.
Thank you, Vivek, for the introduction. Hi, everyone. Good morning and good afternoon and good night if you're in Korea.
Jingjing,
yes.
before I start, I just wanted to clarify. Stephen Chiu is my PhD student, so
Yes.
we also collaborated. Okay, that's all.
Yes, I will introduce all my co-authors. So, my name is Jingjing Zhang, and I know the Crunch group led by Dr. Kanadakis has been very impactful in the areas of PINNs and neural operating learnings, and that also kind of motivate my early interest in this area as well. So today is my great honor to present my PhD research on PINNs application in the challenging multiphase flow problems in subsurface energy systems. Specifically, we are looking at gravity-induced dual shocks, interface solubility, and stratified CO2 migration problems. And this presentation is based on my two published papers, and I've listed them on the bottom here. So if you're interested, feel free to take a look. And I want to introduce my co-authors for these two papers. They are Stephen, although I think he's not here, but Stephen and Professor Dr. Braganato, they are from the electrical and computer engineering department, and Professor Eduardo Gilding of petroleum engineering department of Texas A&M. They all made great contribution to the work I'm going to present today. All right, I have a brief self-introduction as well before we really begin. So I was born in a petroliferous basin of China, that city called Chengdu, and that kind of motivated me to study petroleum at the very beginning. So I got my bachelor's degree from China University of Petroleum, Beijing. And after that, I went to Texas A&M University to get my master's and then PhD degrees in petroleum engineering. And I just graduated this August, and I will join Chongqing University of Technology and Science soon as a faculty member. And during my PhD time, I also had some hands-on experience within the industry. I interned at Kinder Morgan, Chevron, and ExxonMobil, these pioneer engineering companies. So you can tell from my background that I am a petroleum engineer. My main research focus is in the area of general reservoir simulation problems. I do in water flooding, enhanced oil recovery techniques, especially now we are focusing on unconventional reservoirs. And also recently we start to look at new energies such as CO2 sequestration, and also some discrete fractional network modeling and developments, etc. And as a petroleum engineer, we noticed that during past 5 or 10 years, the scientific machine learning has emerged as a powerful tool in the realm of science and engineering. So we start to look at the physics-informed machine learning application in our industry. So today, my presentation would not cover like the development or like algorithms of PINNs, but we will focus on the application. How can PINNs be applied in the realm of petroleum engineering industry? And I know you are all experts in the area, so I don't want to waste too much time on elaborating on the basic concepts, the neural operators, and automatic differentiation, how does it work? But I will give a brief introduction, then we will go straight to the point we are going to solve. So we know that as a petroleum engineer, we have already developed very sophisticated reservoir simulators to help us to understand the physics underneath, what's happening in the reservoir, how oil flows, how gas flows, how to get as much as hydrocarbon out of the reservoir based on our understanding. However, we also noticed that as more physics we add to our reservoir simulator, the more computational cost when spent on it, and it is too expensive to afford now. So we are trying to leverage machine learning method as like a balance between data-driven and physics-based models to help us to solve our modeling problem. And among all kinds of physics-informed machine learning methods, today we are talking about PINNs, which encodes the governing equations into the model's loss function. And of course, we are not only doing PINNs because, for example, Stephen and I, my co-authors, are probably also exploring neural operators application in our study. But today, I will only focus on PINNs. So when I say governing equations into the loss function, I mean a specific model that is Buckley-Leverett model, and we also call it BL model. And I will use this picture to help you understand what a Buckley-Leverett model describes. So it describes one-dimensional two-phase flow problem in the subsurface systems. And we can see that there is a vertical well here injected into the reservoir trying to produce. However, that high expectation will never met that we will drill a well and let it flow by itself and we can get out all of the oil. That's not the reality. So usually we will add some techniques such as water flooding and polymer flooding to help this process. So what do we do is we will drill an injection well near the production well and input some waters or other material, but here we are meaning waters inside of the reservoir, trying to push the water towards the production well and help the oil to move out of the production well as much as possible. So this is a displacement process. And this displacement process can be described by the mathematical equation here on the slide. So we know BL equation is derived from mass conservation and Darcy's flow. And we can take a look at this small element represented by the gray box here with a distance of delta x. So for the water comes in the system, comes in the element, and the water and oil comes out of the element, we can use this PDE to describe this physical phenomenon. And in this PDE, SW represent water saturation. Of course, water saturation is the solution we are trying to solve by solving the PDE here. And if we are using a more general form, we will use this U to represent SW, because later on you will notice that we will not only solve water saturation, but we also can solve gas saturation if it is a gas displacing liquid process. So this is a more general form, but they are basically the same. And T and X are dimensionless distance and time. And on top of the PDE, we also have an initial condition which saturation everywhere is coordinate water saturation. We use SWC to represent coordinate water saturation. That represents amount of water that cannot be removed from the reservoir anyways. And also we have a boundary condition. So at X equals to 0, we have an injector that keep the saturation equal to 1 minus residual oil saturation all the time. And the residual oil saturation also represent the amount of oil that will stay in the reservoir and cannot be removed anyways. And we also notice there's the FW, which represents the fraction flow, or we call it flux function in numerical analysis. And this flux function are very important. We can take a closer look at its expression. And the S represents effective saturation, which is calculated based on the water saturation and conated water saturation and the residual oil saturation. By the way, conated water saturation and the residual oil saturation are known parameters. Only the SW are the U we are trying to solve. And also, when we consider a dip, I forgot to mention the alpha is a dip angle. When we have a dip angle here, we have to consider the gravity effect. And this effect can be accounted in this N, which we call it gravity number here. And this gravity number times the sine alpha represent how gravity dominates the fluid process. And we also have a mobility ratio, which is calculated as the mobility of water versus the mobility of oil. And we can use this like relative permeability and the viscosity of two phases to calculate mobility ratio. And I know probably as a scientific machine learning user, it is kind of overwhelming and confusing for you, but you don't have to understand every parameter here. You just remember this gravity number, this mobility ratio between two phases can control the characters of flux functions. So we have all kinds of flux functions. But now I'm going to present one of the most classic type of flux function by this dashed line here in the A subplot. So this dashed line is F flux function versus water saturation U. And if we look at the BL equation at this dashed line here, we will notice that BL model is a nonlinear hyperbolic PDE. In addition, it is accompanied with a piecewise initial condition. And in numerical analysis, we call this kind of problem the Riemann problem. And for Riemann problems, we know that there can be multiple weak solutions for these problems, and only one of them is physically admissible. We notice this problem, and we can tell, I can explain what do I mean. So if we use this dashed line to solve this PDE equation, we will get a solution profile on the right-hand side shown by this dashed line here. This, on the right-hand side, it's a solution map, a solution profile. X-axis represents the distance, y-axis represents the saturation level. So we can see from this dashed line here, which is obtained by this dash original flux function. If we draw a vertical line, which means at a specific location, we will have two intersect, which means we can have more than one saturation levels, and that is non-physical because for one location, we couldn't have two saturation levels. So that's what I meant, like for the Riemann problems, the solutions can be weak and can be multiple, but only one of them is correct. And other study, we are not the only one who study BL equation. We noticed there are other studies, including Flux from, I think, Stanford, if I remember correctly. What they do, how do they solve this nonlinear hyperbolic PDE is they are adding a diffusion term to this PDE. The diffusion term is a second order derivative to get an approximate of the nonlinear PDE. However, while we do admit it is one of the methods, but we believe it is not the best answer because you are trying to change the original equation, change it to another type and to approximate the solution. So what do we do is for Riemann problems, when we explore the numerical analysis literature, we found they use additional physical constraint to construct the original flux function. And they specifically, the imposition of this ranking Hugoniot jump condition and entropy condition of omelinic on the flux function can help us to select the unique and proper solution for such problems. And the entropy condition can be expressed by this equation here. It ensures that the rarefaction wave trailing the shock does not exceed its propagation speed. And this constraint aligned with the second law of thermodynamics, which dictates the entropy is an isolated system should not decrease. And the Rankine-Hugoniot jump conditions ensures that mass conservation across the shock front by equating the fluxes on either side of the discontinuity. And this condition determines the velocity at which the shock propagates. I know this kind of probably sounds also confusing for you, but our previous researchers are so smart, so they developed a geographic method that can help us to understand these two compositions quickly. So we can notice on these two plots, we have on top of the original flux function, we have another solid line here, and that it represents our constructed flux function after imposing these two conditions. We noticed starting from the point, if we draw a tangent line here, and the intersect would be a UF, which is the shock saturation, and FUF. And this before this intersect, this original dashed line will be represented by the convex hull or concave hull in some circumstances. And behind that point, we will keep the original flux function. So in practical, in PINN, when we construct PINN code, I will use this solid line to replace the dashed line to input in the loss function of neural network. Because based on our understanding is if you input the original line, it itself will result multiple weak solutions. And then if that's the case, how you can expect PINNs can give you the one unique proper answer. And that's not fair for neural networks based on my understanding. So we will input this constructed flux function into the neural network to let it train. And this constructed flux function will result a solid solution here shown on the right-hand side, which is also represented by the solid line here. We can notice there's one shock wave here represented by this vertical line, and it is followed by a rarefaction wave here from UL to UF. Okay, now that's the dynamics of the problem we are going to solve. Now let's take a look at the training. So for training, we use very basic structures of like multi-layer perceptron. It's a small structure, and initialization and optimizations are very common. And we don't add any data to train. We only have the PDE laws, boundary condition laws, and initial condition laws, and everything else is simple. And another small point we noticed that is that since saturation is the value we are trying to solve here, and it only varies from 0 to 1. So instead of using 10 or don't put any activation for the output layer, we use sigmoid for the output layer to regulate the saturation output range from 0 to 1. And we can see the comparison, this is showing a 3D saturation map. The Z-axis is the saturation level and versus time and space here. If we don't add sigmoid, we will have this non-zero below zero non-physical solutions. But if we use sigmoid, we can regulate this and increase this training accuracy. So we want to take advantage of as many prior physical knowledge as possible. So just reduce any non-zero values here. So by employing this very simple, like we call it vanilla PINN structure and our constructed flux function, we can just simply get very good results. I show this training revolution here. So in horizontal direction, I'm showing a few time slots, t equals 0.1, 0.4, and 0.9. And our exact solution is represented by the blue solid line, and PINN's prediction is represented by this red dashed line. We can see that as more and more iteration goes, simply after around 5,000 iterations, PINNs can already did a very good job on matching the exact solution. And it did a very good job at shock front, at discontinuity everywhere. So we are not using any fancy training algorithms, but simply input the constructed flux function, and then we can get very accurate results. And of course, in my paper, I did more sensitivity study, examining the mobility ratio and gravity effects on this oil recovery, but it's not the central point of today's presentation, so we'll just ignore that part. But if you are interested, feel free to take a look.
Jingjing, can I ask a question? So here you use the vanilla pin, or you use adaptive weights, or what? I know you change the flux. You change the flux, so you have the solid flux, the
Yes.
Convex flux, but what else did you do?
Nothing. Just use vanilla pin and construct flux function. Yeah, and that is the most base case. So we only have one shock here. And now I want to move to more complex scenarios where we have two opposite shocks. So this is the vertical equilibrium process where only gravity take effect here. Imagine we have water in the upper layer and oil in the lower layer. Due to gravity, they will have this equilibrium, vertical equilibrium. And this process can be described by another flux function, which is still can be described by the previous PDE, but the flux function's type is a little bit different. So it can be described by this equation here. And we use the same construction method on top of the original flux function. So same, original flux function is represented by the dashed line, and we use constructed method to construct this function, and we use this solid line to be inputted into neural networks, and we still use vanilla pin and get very good results here. So imagine now I'm showing you a 2D saturation solution map. So the color represents the saturation level from 0, which is represented by the red color, to 1. So because we think which is the blue. So we have water at the bottom and oil at the top, and they are propagating through the opposite directions. And there are two shocks in this case. And we can see vanilla pin managed this very well. I forgot to put a specific training error and loss here, but they are very small as the previous one. So we think not only one shock case, vanilla pin can also handle the two opposite shock case with correct constructed flux function. And we have the third case, which is another dual shock case, but in this case, the two shocks traveling in the same direction. So previously they travel in opposite direction. Now they travel in the same direction. And I will use a CO2 injection process to describe this process. So it is from another literature, but they introduced this retardation D factor to account for the partial solubility between CO2 and brine. So for this case, we are injecting CO2 in a supercritical state, and it's displacing the brine. And due to the solubility, we see that the flux function changes. So the flux function now are showing by this blue line here. And same construction method, we follow the second law of thermodynamics. We follow the entropy conditions, and there are some details of numerical analysis, but we have constructed flux function for this dual shock models, and they are represented by this blue line here. We can see there are two shocks. One is trailing shock, another is leading shock. We can also tell from this diagram here. This leading shock is caused by the different phases, and the trailing shock is caused by the partial solubility between these two phases. And And these two slopes will represent the velocity at which two shocks travel. And we use this constructed flux function and banana pin to train. Still, we got very good results. We can see for two shocks that are traveling in the same direction, banana pin can handle them. Of course, as petroleum engineer, we don't want to just say, okay, we match this, we match this. We want to take advantage of it. So we apply it to a specific case where like our reservoir properties, rock properties are shown here. And if we inject CO2 for like 4 square meters per day for 30 years, we can use the PINN solution to approximate how far this CO2 plume travels in our reservoir, which is after the leading shock will travel up to 1,000 meters, while the trailing shock really, they travel very slow. They only goes as far as 70 meters into this aquifers. And that's how we can utilize it. And we noticed that.
I have a question, because we also utilize, when we solve the Euler equations, which is for high-speed aerodynamics, we also employ the entropy condition, but we employ it explicitly. We don't change the flux.
Oh.
So have you tried to do that? Have you tried to just use the original flux, but actually impose the entropy condition to see if there's equivalence in the solution?
I'm not sure if you're meaning like, I know for subdomain pains, they ensures that by adding another loss term, like
No, not subdomain. Just maybe Raj, if you're listening, maybe you can describe what you're doing exactly.
Yeah, means we did some work for the Euler, the sort problem. So
for the sort problem,
we have a physical and numerical entropy. So where you just make sure the entropy is, if it is 0, then it's positive, then you're violating it. So we just put the penalty for that. So for Euler equation, there is a well-defined physical entropy conditions. So that you just add in the loss function. That is what we did for Euler. But I'm not sure for your equation, like if there is any physical entropy defined.
No, I didn't doing the entropy solely. I just put them into the construction of flux function.
You show the entropy condition for this problem.
Yes, that's why I saw that there's entropy condition you mentioned, but that seems like it's Rankine-Higuenot jump condition, not exactly the entropy condition that is.
No, not the Rankine-Higuenot, the first one. Jingjing, can you go back, please, and show the...
Yeah, this one. You see that this is the...
Olenek, yeah.
Yeah, Olenek, this one.
Yeah, probably we can discuss later about like more details, but
it can be imposed.
Yeah, it can be, yes.
So you can put an epsilon term or something.
Yeah.
Is it possible to actually instead do this convex hull in the Euler problem, the sort problem?
The system, so it's a little more difficult, but to change the flux, because for example, the temperature has a rarefaction, but the density does not.
I see. So maybe that's specific to this particular PDE.
Yeah. But the question is sort of the opposite, right? Because for this is a scalar, if you could actually impose this entropy condition directly and see if that with the original flux. That's what my question was. But anyway, Gigi has graduated, so she's not going to do it.
Yeah, that's for the next student.
Yes.
I'm also interested in exploring more.
Okay.
I will talk to trying to understand more your question later.
I think it will be for the students of Jingjing now.
Yes.
Oh yeah, probably. Oh, glad to mention it. That's a good direction.
Please go on. Sorry for the interruption.
No problems. So yeah, that's actually just a startup. That's based on my first paper of PINNs, and I want to show that we solve like Buckley Leverett with the construction of flux function and the banana pin, and we achieve very high accuracy. We are not using any fancy training algorithms. And also, not only one shock, but dual shock pins can handle that. And in that paper, I also did some like inverse training, but just show how capable pins are, but they are not the focus of today's presentation. So it's already 30 minutes. I'll just jump into the more complex problems we solved using the pins. So which is the CO2 sequestration and like in deep saline aquifers, in stratified deep saline aquifers. So from that, the first study to this one, we want to solve a few problems. One is, so now we are only focusing on CO2's injection into brine. So we want to know, will this injection rate and gravity influence CO2 migration? And we also want to know, since we are not looking at homogeneous media anymore, we want to look at some stratified media of rocks, which is very common we found in the saline aquifers. How does that impact our CO2 migration? And are banana pins still capable of modeling this more complicated process? So the second paper trying to solve these problems. And I want to give you a brief like background review, like geologic carbon sequestration is very helpful for us to reduce the mitigating climate change by capturing and storing CO2 emissions. And potential sites including deep saline aquifers and unminable coal beds, as shown on this picture, and also depleted hydrocarbons. But among these, deep saline aquifers are still the most abundant globally. And however, there are a lot of uncertainties with them because usually they are lack of prior monitoring, and we want to take a look at them. And in deep saline aquifers, sometimes we observe thin, less permeable layers exist, such as this seismic survey shows. They are these layered structures which sometimes made of mudstones. They will affecting CO2's vertical ascent. For example, this Sleipner pilot site in North Sea, which is world's first large offshore carbon capture and storage facility, they monitored using microseismic technology like the profile of the saline aquifer reservoirs from 1994 to 2002. And we can see as time goes by, and the IP represent injection point. As time goes by and this CO2 goes up and they are trapped by these lateral barriers. And I think they are relatively impermeable mudstone. And finally, at the year of 2008, they reached the bottom. They reached the top. And a similar phenomenon has been observed in this deposit in southern Louisiana, which they draw this study. They draw a concept of diagram to compare. So on the right-hand side is the observation they found, which is composite confining system, and on the left-hand side is a like more convention seal we think it should be. So we think conventionally, we suppose there should be a perfect seal which stops CO2 from leaking, and we call it cap rock. In reality, that cap rock, we don't know if it exists or if it's perfectly sealed. So they observe this multiple thin layers, and probably there are 5 to 15 mudstone layers per 100 meters according to their observation. So solving the CO2 dynamics in the composite confining system becomes the interest of the study. And let's do a quick review of the dynamics in homogeneous, which is the one we just presented. We have fraction flow model, and now we are adding an injection velocity. So the flux function is a little bit different, but actually they are similar. So we have a total velocity here, which represent our injection velocity. And also we have a G represent that mean ascent velocity here. G can be an important parameter that can help us to characterize the driving mechanisms. So For the CO2 injection process, we think there are mainly three types of driving mechanisms. One is injection driven, which means we have very large injection rate. And the zeta, which is velocity divided by g, is much larger than 1. And that process can be described by the Buckley-Leverett equation we just mentioned. We ignore gravity here. And sometimes when gravity and this injection combine to dominate this, jointly to dominate this process, we think theta is almost like around 1. And we introduce another equation, which is BLG equation, to account for this joint process. And when theta is much smaller than 1, we think this process is purely buoyancy driven, only gravity plays effect. And we can use vertical equilibrium equation to kind of describe. Actually, we have mentioned all of three types previously, but now we are just doing a more systematic summary. And this is the flux function of these three types of driving mechanisms. The original flux function are represented by the dashed lines. And similarly, we use same construction method to construct. And they are represented by the solid line, and they will be inputted into pins to train. Very classic. And since we have tried that before, so I don't want to waste more time, this is the saturation profile, how it looks like. The dashed line where we have this initial condition, if it's like injection driven, this saturation front will propagate very fast. And if it's not purely injection, then we will have two shocks here traveling in opposite direction, and they will be connected by this railway fraction wave. So in homogeneous systems, we know this is how the profiles look like. However, in stratified systems with permeability discontinuities, the flux functions has a spatial discontinuity, and that Riemann solutions contain an additional stationary shock at the interface will make this profile more complicated. So I will give you, this diagram will help you understand what's the problem we are looking at. So we consider two scenarios. So we think CO2 travels through this vertical column, and we consider two primary scenarios. One is on the left-hand side, CO2 migrating from a high permeability, a low permeability side to a high permeability side, and vice versa. It travels from a good permeability to a bad permeability rock, and there is an interface, which is represented by Zi. And our initial condition is in below Zi, we have one saturation, and on top of Zi, we have another saturation. So the governing equations for CO2 saturation will have this two for each layer, for lower layer and upper layer. And here, F and left and right is not exact. So left means lower layer, right? R represent upper layer. So we just use numerical expression. And that's the governing equation, and that is our initial conditions. And of course, we at the interface, we impose the Rankine-Hugoniot conditions again. We want to ensure the flux continuity across the interface. So we have this FL, which is the SL is the saturation we get from the upper layer towards the shock, and SR is the saturation level we got from the upper layer towards the shock. And when they are close to the shock, we ensures that the flux is equal to each other. To ensure physical admissible solutions, non-stationary waves must satisfy entropy condition as well. And additionally, we have a stationary shock at the interface connecting SL and SR must satisfy the in entropy equality. So this is also kind of confusing, but we do come up with the geographic construction let you understand what we have inputted into PINN, which is the red, which is the green solid lines here. So I summarized 6 scenarios, which is buoyancy driving and mixed driving and inject driving. And under two scenarios, one is good rock travel to bad rock, another is bad rock to good rock. So there are in total 6 scenarios we are modeling here. And we can see that. So if we travel from a good rock to a bad rock and the theta is much less than 1, then we will have these 2 dash lines first, which the dotted line represent the lower level flux function, and the dashed line represent upper level flux function. And the constructed flux function is represented by the green line, following the equations we just mentioned on the last slide. And we notice it is very complex. It comes with like 1 shock, 2 shock, 1 refraction wave, and another shock here. And more importantly, it is multi-value, which means it's impossible for one neural network to solve. So for this kind of flux function, we adopt subdomain PINNs to solve each piece. So for this piece, we have one neural network. And for this piece, we have another neural network. Each of them dominates one layer. And similar thing, we see the first one and second one have similar shapes. So they are treated with the same, and also the first, actually the upper column, they are called multi-valued flux function, and they will be taken care of by subdomain PINNs. And the lower level, it's the vice versa situations based on the top one. So the top one has KL larger than the KR, but the bottom one is like contrary. So we travel from the bad rock to the good rock. And that is our construction of the flux function, which now we notice they don't have multi-value anymore, but they are more piecewise, they are shattered. So they have more discontinuity, 1, 2, 3 shocks and 1 refraction wave here, very complex. And we found that, just to mention at the very beginning, we found that vanilla PINN are not able to handle them. So we adopt self-adaptive PINNs to solve the bottom 3 scenarios and use subdomain PINNs to solve the top 3 scenarios. And I'll just directly jump to some results. But before that, I use 2A, 2B to represent each of them. And I will have a small summary here later, probably. Summary for each of the cases about the initial condition, the rock permeability, and the injection velocity. But there are 6 cases we are modeling here. And of course, I want to remind us the baseline PINN is very simple without data. The subdomain PINN has divided the whole domain into small subdomains, and we have the continuity loss to penalty any difference at the interface. Similar, like within subdomains, still we have residual loss, initial condition loss, and boundary condition loss. And self-adaptive PINN was developed by one of Dr. Buckley's students in 2003. We found it is a very helpful tool to help us to capture those stiff areas, especially when we have multiple discontinuity in our 3 scenarios. And that's the PINN algorithm we adopt. On top of that, yeah, I think we don't have to elaborate on, since you are all experts, I just simply use this subdomain PINNs. I divide it into 2, specific, I'm using 2. So 1 for the good rock, another for the bad rock. And I add this interface loss bit at the interface to ensure and to let it train to that subdomain PINN. And self-adaptive PINN is also very helpful, and it used the gradient ascent optimizations to add more weights to the points that has higher loss. And we can see this omega, the vector represent the weights we add onto the training points. These are methods. And as for the training framework, and same thing with the previous one, we use a simple MLP. We use simple initialization, but at this time, we are trying to for some of the cases, not all of them. Sometimes we found LBFGS helps a little bit to reduce the residual loss to a smaller value. And also there are other training tricks, but overall we are managing to use these three techniques to model all the process. And I will skip this warm-up case. We don't have time for that. Let's jump into the case 2A and 2C, where we have if you can recall, where we have multi-value flux functions. We are using subdomain PINNs to solve this problem. And here I'm showing a 3D saturation map. And the left one is the exact solution, and right one is our PINNs prediction with very low error values either for case 2A or case 3A. And we can see this saturation map is very complex. We have some shocks here and rarefaction wave here. And that is the loss evolution during our training. We can see subdomain loss 1 and 2 and interface loss. So basically subdomain help us to solve this problem, and we achieve very high accuracy. And then I want to go back to take a look at what does this mean to us petroleum engineers. So I pull out the saturation map in a 2D view. The x-axis is our distance in z direction. The y-axis is our saturation level. And if we compare two scenarios, so if we have initial condition here, which is represented by the black dotted line, and for inhomogeneous, the CO2 will propagate like this, which is represented by the green dashed line. It propagates upwards very high, very fast. But if we travel from a good rock to a barrier rock, mudstone layer, we will see the saturation map will look like in this red dashed line. And this comparison can tell us this barrier acts as this rock disperse the CO2 plume, and it reduces gas fluxion entering the low permeability region, and it helps us to accumulate CO2 beneath the layer and reduce the risks of leakage on the top. And that's the comparison between the CO2 propagation in piecewise and homogeneous reservoir, and that is meaningful for us reservoir engineers. And now we switch to the self-adapt PINNs, and for case 2B and 2.3, remember they have only single value, but there are several pieces. So first of all, I found the vanilla PINN doesn't work. It doesn't work at all. First thing is I do a grid search to tune the learning rate. I found there are several combinations of learning rate and beta 1 and beta 2. I found a slower learning rate is essential when we study a more complex process. So previously, I think I'm using like 4e-4 something, but now I have to drop it to 1 order of magnitude lower. And we found this learning rate and beta 1 equals to kind of 0.85, and beta 2, I think it's 0.99. I forgot, there's a specific number. We find it's an optimal combination, and that is PINN. However, this tuned rate is still insufficient for us to capturing. We can see this arrow heat map, which is in a 2D view, we have a t, time, and z, which is the distance here. And we see this arrow is very obvious at the shock front. We see 3 straight lines there where our shocks at. So it means it did not capture the shocks very well. It remained poorly captured and necessitating further refinement. So we introduced self-adapt PINN, and that is the weight we obtained by employing self-adapted PINN. We can see the color and size of the scatters represent our weights for the training points. We can see they are very obvious at the shocks, which represent the neural network learn itself, though they know that the shocks are very important. So they automatically add more weights on this area. And finally, we get very good results. And this, using this box plot to compare how good it is. So I'm comparing 3 training algorithms. One is baseline PINN, another is the one we have tuned learning rate and beta. And the third one is SAP-PINN. We know by observing the training loss for case 2B and 3B, we found that tuned learning rate help to reduce the loss and error a lot. However, SAP-PINN help us to refine it more. So SAP-PINN is very robust and very helpful training algorithms for us in terms of such problems here. And finally, I just want to do a brief summary. So this slide summarize all the solution profile we have solved by utilizing PINN, vanilla PINN, self-adaptive PINN, and subdomain PINN. We can see all of them did a very good job. The initial condition is the black dotted line, and the exact solution is represented by the blue line, and we have PINN's prediction in red dashed line. There are multiple shocks and multiple probably fractions, but our PINN can all capture the discontinuity and shocks very well. So that's kind of meaningful for us. And finally, we get some learnings from this, how to train. There are some small tricks, and more importantly, my study aligned with the field observation from the Slipner side. They observed the CO2 reach the top of the 200 meters thick aquifer around I think 20 years. So it is consistent with our study. That's pretty much. I think I kind of go over time, but yeah, feel free to ask any question. I also want to mention that now, as engineers, we also found that PINN has its limitation. Like for example, we spend a lot of training efforts just to solve one problem. So Stephen and I are also probably will work on the neural operator to solve more problems, hopefully. Yeah, thank you.
Thank you, Jingjing, for presenting your work. We can now open the floor for questions to Jingjing.
Jingjing, maybe you can tell us some of the cases that you wanted to solve with pins and you couldn't. Some failed cases. Because we are in applied math here. We are interested in things that don't work. I'm glad they work for you.
Yeah. Yeah, I noticed there's a previous seminar presented on the failure pins cannot achieve. I have to say it's not okay. There are one case that is extremely painful for me. I didn't show it on this presentation, but when I do the inverse training, I was trying to train 2 parameters. Let me go back to probably I can go back.
I think one of the main issue with pins is really the time, the time to train it, the time to fine tune it. I mean, that's really, we have spent 60 hours training a pin. I mean,
Yeah.
so.
But now we have the agents, right? I don't know if you've seen our papers on agentic scientific machine learning. The agents take care of all this. We don't need graduate students. We totally eliminate the graduate student, even the postdocs.
Well, I'll take a look at that.
So take a look at scientific
Hopefully not
machine
the
learning.
current ones, only the future ones will be.
Yeah, no, it's good that the Jingjing has graduated, but I'm just saying that the scientific agentic scientific machine learning that we have published, and another one, Athena, basically do all this systematic. The agents iterate, collaborate, and so on. They give you the answer while you're sleeping. You get everything.
I have to take a look at that.
Yeah, we get a superhuman performance on all basically tasks. So
is it a recent paper?
yeah, there's a couple of papers. Maybe Kyle and Juan can put their papers on the archive, and Varun is done something for design in case you're interested in also design. But there are 3 papers on agentic stuff, and DARPA is preparing for a big project on that.
Oh my.
Yes.
Yeah.
Actually,
Specifically on the mathematics of scientific computing, scientific machine learning. Yeah.
yeah, actually, it's a bit interesting because I see that here Jingjing is, for example, I asked it the agents I put it on the chat to solve the implicit Borger's equation. Of course, it's much simpler than what Jingjing was doing, but it's funny that Jingjing found that they had to impose this entropy condition, and then they did it consider the left and right points. But the agents found something similar. They found that they imposed the entropy conditions as a soft constraint, and then they also combined it with vanishing viscosity to solve the problem. So it's kind of interesting because
both things that you mentioned, yeah.
Well, that's very.
I actually put it on the paper. Yeah,
Ulysses also the Athena framework is kind of general. So Juan asked the agents to solve the implicit 2D Burgers equation. 2D Burgers equation.
2D, yeah.
And they actually found an exact solution.
Wow.
I didn't know that there's an exact solution, but they did a transformation, and then they did methods of characteristics, and they got the exact solution. We expect them to use pins or DG, discontinuous Galerkin, but they didn't do that. They solved it analytically instead. They have a mind of their own.
Wow.
It's a little scary, but
are you using some API to a large language model, or is it
multiple language models, all of them, and then there's strategies on how you control them. There's different things you have to see what's going on in the papers, but the point is that actually Jingjing went through this process and documented that in the paper. That is public knowledge that will go into these knowledge graphs that we built, right? So the next time around, probably the agent will choose to use convex fluxes, approximate the fluxes, and solve the problem instead of taking the viscosity to 0 or trying to do something else.
So George, as a clarification, so the time to computation is the same, but it doesn't require any more someone to actually be there, right? Is that what the agent does?
Yeah, the agents try different things, and then they argue and they collaborate. Just like you would do with Jingjing, right? And then the 4 of you when you wrote the paper. Something very, very similar, actually. But it's unfortunate that we cannot publish in the papers all the intermediate dialogue that goes on between the agents, because it's very funny and very insightful, the intermediate results, not just the black magic at the end. The intermediate results of collaboration is kind of interesting. And they can, like the ablation studies and so on, that could also be part of this. But
wow.
This is just a snapshot of what's coming up. 2025 is the year of agents, but a study like this, I could see that since it's published, Gemini 3 and so on would know about it. Right. But in the other paper we show, because we published a paper last year on a single agent, right?
Right.
If you just ask Gemini 3.0, for example, what would it do? It does a good job, but Kyle, the other paper, showed that the multi-agents would improve the solution of the single agent by a factor of 10,000, for example, for the Burgers equation.
Yeah, that's amazing. I wasn't aware of any of this. I mean, I have to look at this. Yeah. I was talking to a friend of mine about 5 years ago about doing something like this. But
even last year, they were not ready. That's why we show our study from last year to this year. But in the last few months, there have been some great advances in reasoning.
Wow. So, and you don't have to engineer a prompt or anything, I mean?
No, there are prompts. There are prompts, and there's assigned roles and so on. It's like how you actually So, I mean, what we did is we sort of tried to do what we do in the lab with the students, the postdocs, and so on. There's some hierarchy. You can control the creativity of LLMs by controlling the temperature. There's a factor there. It can make them being very wild or very conservative.
Wow.
Okay. I don't want to take away from the work of Jingjing, because I'm glad we had this presentation today, because a few years ago was Eduardo, who is your counterpart at Stanford? They did the BL problem.
Lou Dulowski?
Not Lou, the Iranian guy.
Chalapi.
Chalapi was kind of attacking pins, and then in order to then write a paper on how to do. And I said, the vanilla pin, you have to do something. And I'm glad you solved the problem using the transformation of Flux and then vanilla pin. It shows something. But there are many different approaches now. Of course, the BL problem is. But it's a good test. I thought
I was very impressed, with the performance of pins here. Yes,
the Flux is a wild Flux, actually. I mean, especially with the second part of the talk, where you have it's amazing that it's a scalar equation, because in the Euler equations, I know you can have different structures like that, but it's interesting to see
it is a good feather on the cap for physics informed machine learning. So not everything has to be data driven. I mean, we can still have physics informed.
That's true.
Yeah. Okay.
Vivek, maybe you can ask them again if they have any question in the meantime.
Yeah. Do we have any further questions for Jingjing? If not, I'd like to thank Jingjing again for presenting her work, and thank you, Jingjing. Maybe Junhyong, could you please start sharing your screen?
Okay.
Thanks all for the invitation.
Thank you.
Thank you.
Thanks for taking your time.
Soon, George. I have to look at that. Okay.
I'll be glad to take a look at the data.
Okay. Yes.
Okay. All right. Take care, guys.
I need to drop to another call, but wishing you all happy holidays.
Yeah.
Thank you.
Thank you.
Yes. Thank you. Bye.
So the second talk is from Junhyong Lee on leveraging multi-agent LLMs for intelligent design and manufacturing, from materials discovery to process optimization. Junhyong Lee is a PhD candidate in the Department of Mechanical Engineering at KAIST. His research focuses on large language model-based multi-agent systems for material design, scientific reasoning, and manufacturing process optimization. His recent work includes developing LLM-driven multi-agent frameworks for knowledge transfer in injection molding and designing condition-aware generative models for double perovskite materials discovery. He is broadly interested in integrating simulation, domain knowledge, and agentic LLM workflows to enable intelligent and autonomous design to production pipelines. With this brief introduction, I invite Junhyong to present his work.
Yeah, thank you for your great introduction. And I'm really great honored to present here about large language model agent. And my name is Junhyong Lee again, and my advisor name is Professor Seung-Ha Ryu. And now I am in a PhD candidate program at Department of Mechanical Engineering, KAIST. My title is Leveraging Multi-Agent LLMs for Intelligent Design and Manufacturing. And these are contents of today. First, I want to share the strategy of using large language model into materials and manufacturing with my perspective. And second topic and first topic and the second topic might be the summary of my recent work applying multi-agentic LLM into the manufacturing or materials application. Yeah, large language models have been developed a lot, and their inference capability have followed the human expert level. And there are many open models like OpenAI, ChatGPT, Llama, Gemini, or Cloud Sonnet. My question as a mechanical engineer was that how can I use such large language model for design and manufacturing, and what will be the role of LLM in the field? So I wanted to start from the fundamentals. My question was, what is LLM? It was simply deep learning model trained by a large language data set or corpora, and illustration like this. And their form has been recurrent neural network, long short-term memory, or transformer. But basically, most of the open LLMs are transformer-based models, and large language model estimates the probability of the next token given a sequence of input tokens, as illustrated as below. When the input tokens from 1 to t is given to large language model generate as a generative model probability distribution on the output token xt plus 1. We can say that this large language model as a mapping from input tokens to the output token probability distribution. So my further question was that how can we obtain better this distribution for my application? I want to summarize these strategies into 3 strategies. Yeah, the first might be changing data, which is changing here weight of the large language model. The easiest way might be model selection. And there will be more active way like supervised fine-tuning or reinforcement learning with human feedback. And second strategy will be changing X. How can we make better input for the large language model? In context learning, prompt optimization methods will be included in here. And third strategy might be coordination of large language models, information sources, and tools, which is multi-agent system approach, or optimization of that system. So for this talk, I want to share my endeavors to apply these kind of strategies, or part of these kind of strategies into design and manufacturing in 2025. The first will be IM chat, which is injection molding chatbot, and second will be DP optimization or DP design, double perovskite design for materials field. And blue colored techniques are used in this research work, and red color technique have been used this research work. The first topic is IM chat, a multi-agent LLM framework for knowledge transfer system in injection molding. This is the illustration that I want to realize. In the factory, when new worker came to work, they don't know about factory or machine, etc. So I want to make chatbot that can new worker type their question, and this chatbot find related information or document from field, and based on the knowledge, they can generate solution for that query or question. This work has been published on here. Because of time limitation, I cannot deep dive into the research topic, but you can find this paper and get detailed information. I think most of the people here might not be familiar or might be familiar with the word of injection molding, but this is the backbone of plastic mass production. This is the manufacturing process used to mass produce plastic parts, and this is the simple video depicting the process of manufacturing. Basic step will be melting plastic pellet here and injecting them into the mold and giving pressure, finally cooling and solidifying. Yeah, essential components in everyday life and industry are manufactured by injection molding. So I want to mention that it is really important to build effective knowledge transfer system in injection molding because there are lots of considerations for quality control in this manufacturing process. First of all, there are many process parameters we need to control due to its multi-step characteristics. And we also need to consider environmental variables like factory temperature, machine temperature, factory humidity, and machine humidity. And also for new workers, it is really hard to memorize all the defect types and how can you handle those defects time with adjusting specific parameters here. So it heavily relies on workers' expertise, so we need to build a very effective knowledge transfer system. And this was a traditional and conventional way of knowledge transfer system in injection molding industry. A senior worker documentize their know-hows in the documents like defect removal, troubleshooting manual, and new worker get information by reading them. or company made direct relationship between senior worker and new worker and made them communicate for giving and receiving knowledge. But there are two requirements for this kind of system to operate. The first will be definitely knowledge provider here, which is senior worker. And second will be identical language usage between senior worker and new worker. But in recent manufacturing field, especially in South Korea, there have been challenges for these requirements. The first is retirement of skilled operators, and the second is acceleration of globalization. So our idea was that we want to innovate human-to-human interaction-based knowledge transfer system into the human-to-AI interaction knowledge transfer system. We thought that it is possible because pre-trained large language model have a capability of natural language reasoning, or if we prompt well, their logical flow is like human. So our expectation was that if we make knowledge transfer system with large language model, it can overcome language barrier between senior worker and new worker, and it can supplement declining availability of senior workers. And also we can build interactive and user-friendly knowledge transfer so that new workers do not hesitate to use it. And but the remaining challenges have been proposed. The first is that how can we integrate external knowledge by senior worker into the pre-trained LLM? And second question was that how can we integrate extensive data set generated from manufacturing side to the pre-trained large language model? For the first question, knowledge from the senior workers, how can we integrate them into the pre-trained large language model? We could use the RAG method, retriever augmented generation. It is not the complicated concept. When the user query is put to the retriever finds related information from document or database and transfer these found information to the large language model. And large language model receives this information and user query at the same time and reasons based on those information and query and provide a better solution, information rooted solution. So this paper said that with the retriever, it shows lower hallucination rate and higher exact match rate. And second question was that how can we integrate extensive data set from generated injection molding process? We have used LLM agentic approach. LLM agent means that large language model combined with specialized tool or specialized system prompt. So furthermore, there have been multi-agentic collaboration approaches. Multi-agentic collaboration approaches integrated specialized large language model for each topic or for each task, and then let them collaborate. And so, finally, this kind of multi-agentic workflow could solve complex solution more accurate than single agentic method. This is a research overview of my IM chat work.
Can you go back? Some of the prompts, you mix up some of the prompts that they talk about Tesla stock price and so on. How is that related to manufacturing? It seems to me it's a different department, the finance or the investment.
Different, you mean prompt about stock?
If you look at the multi-agent conversations, the top.
Here.
Yeah. I'm confused because I thought this was sort of technical, that the senior worker talks to the younger worker and so on, exchange that information or disseminate, educating. But are you tackling all the fronts? Because
sorry.
I'm confused as to what are you actually trying to do, because if you also have the financial aspects of it, then it's very broad.
Actually, I want to build a multi-agency system related to injection molding. Actually, this is the exemplary figure from a very initiative work of LLM agent. Maybe this figure can give a confused. I'm very sorry about that, but
but you're not actually using that, right? That's what I'm saying.
Yeah,
You're
right.
You're only concentrating on the. All right,
yeah. Sorry for confusion. This is just exemplary work as an initiative work of LLM agent. Yeah.
Okay.
Yeah.
Go ahead.
Yeah.
Please.
This is Thank you. Thank you for your question. And this is the research overview. I want to build a multi-agentic system that can communicate with new worker and having an access to information sources here, and also for the diffusion model. And this diffusion model and knowledge sources are constructed by field knowledges. Field knowledge like manufacturing manual, table for troubleshooting table from senior worker, and extensive knowledge from manufacturing side has been used to train diffusion model here. So when worker asks a question about the injection molding or other stuffs, this IM chat, which is multi-agentic system, can retrieve information from here and can extract the prediction result or generative result from the diffusion model here. So I implemented and realized this concept with this multi-agentic workflow, but because of time limitation, I summarized into 4 steps. Yeah. The first step was translator. Objective of this translator was table procedure of internal workflow with English. And second, we wanted to handle multilingual input from workers using different languages. My prompt is composed like this way. And then if I input some, as an example, some Korean input like this translator module translate this query into the English for the internal workflow and detect what the language is user using now. Yeah. And this is the second step. After translating the query, the translated query was transferred to classifier, and the classifier classifies the queries based on whether it is related to injection molding or not related to injection molding. So for the injection molding, because this is an injection molding chatbot, we need to provide sophisticated response or very accurate response. However, for the general topic like what is the lunch menu or what is the weather, we don't need to make it delicate. So for cheaper solution for not injection molding related question, we just use single agent, React agent. For the like asking weather is all, React agent iterating reasoning and action only using tool of searching API and generating the solution for this query like this way. This was much cheaper than other multi-agent workflow that will be explained later. And for the injection molding related question, firstly, knowledge creation for seniors know-how and manual have been conducted. For the first knowledge, from interviewing with experts in the injection molding field, we have summarized for each defect type, how can he adjust the process parameters like increment, decrement of each parameters or priority for adjustment. And as a second knowledge, we use manufacturing machine manual, which is 200 length page PDF, which contains material condition, maintenance, control guideline, etc. And we have used RAG for created document from knowledge, especially for troubleshooting table and manufacturing manual I mentioned before. These documents are split into the chunks, and these chunks embedded onto the embedding space using Vice library. And then these vectors are denoted as blue dots here. And user query was put to the embedding space using the same embedder here. And when this kind of keywords was given to the retriever, using the similarity search, we have found information from documents like this. And then we augmented keywords and information from document here and let LLM agent to summarize it again. And third is that extensive data set. For the extensive data set from manufacturing side, we have used diffusion model tool calling. We trained diffusion model from data set from manufacturing side, but yeah, as a summary, this diffusion model generates process parameter set using environmental variables like temperature, humidity, and quality. But the most important thing was that the input query is natural language, and we need to extract numerical information from natural language and format it as a numerical vector. So we put one more input formatter here, and then we constructed this kind of pipeline. As an example, when this kind of query was put to the input formatter, this input formatter constructed numerical vector. And this numerical vector was put to diffusion model again. And this diffusion model generated process parameters output like this way.
What's the advantage of using diffusion model here instead of just something simple?
This diffusion model is trained by dataset from manufacturing site, but pre-trained large language model opened by company like OpenAI, Google have no knowledge about manufacturing field. So by using tool calling with diffusion model, we can conduct some quantitative reasoning based on the field knowledge, numeric field knowledge. So if we ask a question of this one to the pre-trained large language model, it does not have access to the data set or the local model we have used. So the answer might not be this kind of numeric form. This just be assumption or textual feedback. Yeah.
Okay.
Thank you for your question.
So I have a question. Hi,
yeah.
Zhang. Can you repeat again what was the role of this diffusion model here? Is like what it takes as an input takes like this set of coordinates. Yeah. So you have like the query, and then the LLM somehow extracts the main variables, and then you send the main variables to the diffusion model. But what does the diffusion model do?
Diffusion model is AI model suggesting process parameter set suitable for these environmental variables and for the quality or class we want. Okay. Yeah. But this diffusion model is numerical or data-driven AI model, and input format is very strict. Here we use 4 environmental variables and 1 quality control factor. So there will be 5.
One question here. So essentially what you're feeding to the diffusion model is like the environmental variables and what are you expecting that will be somehow the quality, and then the diffusion model will tell you how to do it, which will be the process parameters to in other words, the diffusion model tells you the parameters or the rules or the process how to get the achieved quality, right?
Yeah, right. For the diffusion model, it generates process parameter set that is optimal or suitable for these values. Yeah, number values.
And in that case, why did you choose the diffusion model? Because it sounds like it's like you can create there may be a map 1-to-1, right? So why a diffusion model that is like a bit stochastic and not another operator, another network that will be a bit more deterministic?
Yeah, I think so. But this is the one of the case. We can choose any kind of model if we need, but we have chosen diffusion model because actually compared to other generative models like VAE or GAN, in this paper they mentioned that diffusion model has a more accuracy in generation and diversity in generation. So we adopted this one, but we can substitute this diffusion model with any kind of other model because this pipeline said that if we switch diffusion model here, we can just prompt again here. You need to extract required information from natural language query here. Yeah, like that way.
Yeah, okay. And maybe one question here. Okay, that makes sense. Thank you for explaining. And maybe another question here is like, here it looks like the user or the query is actually giving all the information just in some kind of natural language, right? So why not using like a normal, people use for this JSON files or like some kind of structural input, and you just because it looks like the LLM is just organizing things that you're giving it directly, right? So he's not doing any kind of special reasoning for this process. So why do we need an LLM here? That's the question.
Very great question. I skipped that explanation because of time, but if there is some issue when what I mean is that diffusion model these 5 parameters, right? If some of the information is missed here, I want to make this agent to fill that information or ask human that if you can fill that blank. Yeah. So this kind of decision-making process, I want to make this decision-making process automated by this agent.
Okay, but then so it would not be possible to do like a non-LLM method. For example, if you get the information, you can use. I think that in Python there's this thing called regit, which essentially captures. It does essentially the same, but without the API call.
Yeah, right. Yes, I think so. As you mentioned, this process might be replaced to other non-agentic method, but for the expansibility, I think in the future work, maybe this info formatter may do more work than just filling, ask people to fill in here or fill in the blank with their pre-trained reasoning. In the future work, I think additionally, they can find related information about here, or they can check the sensors on the manufacturing site and they fill that form. So considering that expansibility, agentic work might be beneficial, but at now stage, I think it might be replaced to another non-agentic method, as you mentioned. Yeah.
Okay, that makes sense. Thank you. Thank you for explaining.
Yep.
Sorry, I had a question, like a small question on this slide.
Thank you for your question.
So the query is being provided by the user, right? The human is providing the query, right? This query that you have here.
Yeah.
So I assume that like the LLM is extracting the input that goes to the diffusion model. Is there like any check on what inputs are beyond the range of the model? Like if it is like beyond the range of the input that the model used for training, it's just going to generate some output which is like not correct. So is there like a checking mechanism here where you can ensure that the input is within the range of the model's prediction capabilities?
Yeah, you mean the temperature range or humidity range
out
of the
temperature, like you provide 30 degrees for some reason, and the model is just trained up till 26 degrees Celsius. It's still going to give you an output, but it's not going to be correct to some extent.
Actually, diffusion model. Sorry. Yeah. Okay. Actually, diffusion model is generative model, so its generative performance is not guaranteed for the out of distribution, as you mentioned. Temperature range out of the desired range or humidity range out of desired. So the kind of instruction might be given to the user, and
But I think like your LLM here is useful in that way that you can provide.
I think so.
As
that I want to
background
mention.
To the LLM.
Right.
That's how you can make this LLM more useful.
Yeah, I think so. That might be a great idea if I have as some information about intervals of input range here, and let them find or let them feel that. Yeah.
Thanks.
Thank you for a great idea. Yeah. Okay, now I have embedded diffusion tool calling model and retriever into the executors. And then translated query was put to the planner, and then planner plans subtasks to serve that queries like this way. And then executor executes the first task in the planner, and then the generated parameter based on generated parameters or task result and plans and queries, supervisor evaluate whether it's served or not here. It is not served because information polypropylene, which is in the query, was not served. And then planner replan for the remaining task, and executor executes for the only first task here, and then find manual for the PP pressure range. And supervisor will say that yes, because we have generated diffusion model and found pressure parameter condition on the PP materials like this way. This is how we tackle the complicated problems in injection molding related queries. Okay, and this answer was summarized and retranslated to the language the user is using by reporter here, but I skipped the explanation. And this is the demonstration video of the IM chat. I skipped the explanation, but it does have a memory. So when I state about my name here, this query was classified as non-injection molding related question, and reporter will say that, yeah, just like this way. And the response was really quick because we just used single agent for non-injection molding related question. And if I ask that, do you remember my name? And it will find my name on the memory and respond like this way. And the second example was injection molding related question, just for manual retriever. Yeah, if we find the material condition for ABS, this is injection molding related question. So planner will plan how to tackle this issue, and executor finds a manual, and the result will be reported like this way. For the ABS, injection molding temperature range might be this way. This is the manual information rooted solution. And third is diffusion-based parameter generation. Yeah. When the environmental parameters and conditions are given to the diffusion IM chat, it calls diffusion model, and diffusion model generates the process parameters suggested for these environmental parameters like this way and presented by reporter. Yeah, now this is the evaluation of IM chat. So I wanted to check that constructed IM chat is accurate and efficient enough. So I prepared 100 single tool questions, which is solved by using one tool or retriever, and 60 multi-tool questions. For the first analysis, I evaluated accuracy, latency, pricing for three different models, 4.0, mini, and 3.5 turbo. We also compared accuracy score by human evaluator and LLM evaluator. Yeah, as a second analysis, I compared multi-agentic approach versus single fine-tuned LLM agentic approach. Yeah, for the accuracy, we prepared 100 questions for each tools and make Q&A pair like this way. And we have 100 Q&A pairs, and I did for 100 Q&A pairs, we did LLM evaluation and human evaluation. For the LLM evaluation, I prompted please evaluate Q&A pair based on relevance and correctness, and rating should be between 0 to 10. And for human expert, we asked them to evaluate those Q&A pair with the same way based on relevance, correctness, and please rate them between 0 to 10. Yeah, this was the result of human evaluation, and this was the result of LLM evaluation. We can see that high capacity model was better and human evaluation, LLM evaluation showed similar trends. The pure correlation value between human evaluation score and LLM evaluation score was just 0.5. It means that it was not much correlated. So it means that human expert feedback is still valuable for evaluation of such constructed LLM workflow. And this is the latency result, and this is the pricing result. Pricing result was some kind of obvious, but for the latency, 4.0 mini was the highest because inaccuracy of reasoning of 4.0 mini caused the unnecessary iteration of plan and execute workflow I mentioned. And for 60 multi-tool questions, multi-tool question was designed to use diffusion tool and another tools. So I accumulate Q&A pair again. I let LLM evaluator and human expert to evaluate those Q&A samples based on relevance and correctness. This is the result. Yeah, we can see that also for complicated problems. I mean, multi-tool task, high capacity model was better, but LLM evaluator was not identical or similar to human evaluation. So I want to mention that LLM evaluator could not evaluate exactly for domain dataset-based quantitative reasoning, and human evaluation is necessary for LLM workflow evaluation. Also for multi-tool wars, latency and price tendency was
we are not able to see the screen.
Something sorry
happened,
for that.
I guess.
Yeah. Sorry for this. Oh, sorry, my PowerPoint was reset. Sorry for technical issue.
That's all right. Yeah.
Share. Okay.
It works. Thanks.
Thank you. Thank you for waiting. Yeah. And this was the result from latency and price for multi-tool task. But for multi-tool task, diffusion model was mandated to use. So diffusion model usage was the most important factor for latency determination. So the surprising was that 3.5 turbo could not import to use diffusion model. So latency time was the smallest. And price was obvious here too. And second analysis was multi-agentic approach versus fine-tuned single-agent approach. Multi-agentic approach is the proposed IM chat, and fine-tuned single-agent was proposed here. And we accumulated training Q&A pair and supervised fine-tuning the pre-trained language model. And with the only with the single agent, we wanted to cover all these knowledge sources together. So we have accumulated training set like this way and fine-tune GPT-4o model by OpenAI API like this way. I'll skip here. And these are the result for single-tool tasks and multi-tool tasks. Let's go deeper. For the accuracy, multi-agent approach was more accurate than fine-tune single LLM approach like this way. And multi-tool usage was seemingly not able in the fine-tuned single agent LLM. So there is a limitation of handling or retrieving heterogeneous knowledge sources in single agent. So for the heterogeneous knowledge sources, it is very suggested to use multi-agent approach. And for fine-tuned single LLM agent, solve the problem with a single invocation. So it was much faster than multi-agent approach. And communication between agents caused API usage. So IM chat was more expensive than single fine-tuned model. So multi-agent approach showed advantage in heterogeneous information sources, and it could it could generate higher accuracy in quantitative reasoning because we have used diffusion model with true calling. But fine-tuned single LLM agent had difficulty in heterogeneous information sources, and it conduct regression and generation via large language model. It showed lower accuracy in quantitative reasoning. And for the speed and price, fine-tuned single LLM agent was better, and for multi-agent approach, it was worse. So there was a clear trade-off between extensibility in information, accuracy versus pricing and invocation time. So this is the conclusion of the first topic. We have constructed multi-agent LLM-based knowledge transfer system for injection molding, and field-documented and extensive domain knowledge have been integrated into the multi-agentic system. And high-capacity models did better, and human expert remains essential for evaluation for LLM workflow. And there was a clear trade-off between extensibility, accuracy versus pricing and time. In the future work, we may apply hybrid approach using both the multi-agentic workflow. And in that multi-agentic workflow, we can fine-tune some of the single agent among them. And the second topic is, let me see. Well, second topic is LLM for DP materials design, satisfying language condition. I want to make a system that generating double perovskite composition, satisfying conditions given by user. Yeah, this is the importance of material discovery, but it is really difficult because of the heavy computation and a lab experiment requiring human resources, and material design space is not small. It is really vast. And there have been proposed machine learning-based approaches to accelerate this kind of research work. The first direction was surrogate modeling and the combination of that surrogate modeling with optimization algorithm. They replace heavy and costly simulation with the surrogate model and combined with optimization algorithm like genetic algorithm or PSO. They did inverse design for finding material that satisfies such conditions. Second direction was generative model-based materials inverse design using conditional VAE or conditional GAN, conditional diffusion model for finding desired material. It was a promising way of inversely designed materials. However, there have been major challenges by those generative models. The first challenge was it fails to incorporate explicit physical constraints. And second challenge was that it shows poor performance in unseen domain, extrapolation domain, which is called OOD as well. So I thought that there is an opportunity of LLM because they have chemical knowledge to consider physics constraints. In this paper, they tested large language model, open large language model regarding chemistry knowledge, and they found that they found external expert level or more than expert level knowledge in the large language model. So we expect that implicit capture, pre-trained LLM can explicitly capture the underlying chemical grammar for physical constraints. And second is that for tackling extrapolation problem, admittedly, LLM is generative model as well, so they have limited extrapolation capability, but LLM has vast and general training set. So there is more opportunity that optimize will be located within the scene domain by large language model. So interpolation within the in-distribution or interpolation range might be valuable, and it is important to develop those methods like prompt engineering or test time optimization. So there have been research works finding better materials in ID using prompt engineering and agentic approaches in meta-organic framework, alloy, organic, or inorganic materials. And among them, there have been interesting work called text gradient. This is prompt optimization method analogy with neural network. For the neural network, there is a loss term evaluating total neural network system composed of bias and weights here. And there is a signal modifying or giving the signal of modifying the direction of weight and bias here from layer behind to the former layer, which is gradient. But for the multi-agentic system, there can be a loss evaluating the system here. And then there can be also signal providing a modification direction of the components of the former layer by behind layer, like this way. So as a summary, text gradient proposed in this study is feedback about how to change prompt or other components in multi-agent system to improve loss. I want to adapt this kind of concept into the materials design problem. When you want to satisfy conditions here, generator might generate composition that can satisfy this condition, and evaluator can evaluate this condition with a loss. And then gradient engine might give the feedback or modification direction of this composition to meet loss. So text gradient in materials design might be explained as feedback about how to change composition to improve loss. This is problem description. This is kind of optimization problem. So problem might be finding better composition from initial design guided by LLM text gradient like this way on the DP composition space, which is virtual space on the latent space of large language model. The further idea was that, inspired by physics-informed neural network or physics-informed machine learning, if we can give information about physics knowledge or for our problem, material-specific knowledge or data to the gradient, would it be effective or would it be functioning more? Yeah, that was my question. And I have constructed workflow to check effectiveness of knowledge and machine learning from text gradient. So when user query was put to the generator provide compositions, and this composition was evaluated by pre-trained knowledge of LLM, domain knowledge from loss, and machine learning model-driven loss. And based on those loss, text gradient was used to update the next composition generated by generator. So for the first analysis, we checked effectiveness of domain knowledge from text gradient. And for the second, we did analysis for effectiveness of machine learning model-driven text gradient. For the first, we defined three cases: LLM generator with LLM evaluator, and LLM generator plus LLM evaluator plus domain knowledge from evaluator. And this was the target material, which is perovskite, and we design objectives as stability, two metrics for stability here, and perovskite type and compositional condition. And domain knowledge we have used was new tolerance factor, which has been widely used to estimate the stability of the perovskite. If tau is less than, which is new tolerance factor is less than 4.18, it has been known to tend to be structurally stable. So we added this domain knowledge to the gradient for constructing domain knowledge guide text gradient. Yeah, this is case one. When input query was put to the condition extractor, conditions have been extracted, and composition generator proposed composition, and we don't want to find existing material on the materials project. So we constructed tail finder here and make iterations so that this composition generator generates non-existing perovskites. And this generator in case one is put to here for case two, and LLM evaluator give the direction of modification like this way. And for third case, generated composition was put to two evaluators here, and gradient engines modification direction based on pre-trained LLMs knowledge and domain-specific knowledge, and modified like this way. This kind of iteration made totally 150 composition for each case. and for 5 queries, and DFT calculation have been conducted to evaluate 2 metrics related to stability. These are the queries we have used. And we have found that stability has been improved when the domain knowledge-based gradient was integrated, and it was shown that domain knowledge could enhance probability of generating stable compositions in double perovskite. Yeah, it means that formation energy had dropped, energy of overhead had dropped, and fraction of stable materials has increased like this way. And second analysis, we wanted to check the effectiveness of machine learning model-driven text gradient. For each case, we have added machine learning model-based evaluator and their gradient, and we have used machine learning model CRAMNet. Yeah, this is For 5 queries, we have generated 150 compositions as like before, and calculated two metrics related to stability of the materials. And we found that for 5 queries, query 2 and query 5, for the query 2 and query 5, integration of machine learning deteriorated, or it was not meaningful for that integration. But for query 1, 3, and 4, we found that stability energy of overhead value dropped, which means that composition got stabilized because of that machine learning based gradient. So we wanted to figure out what are the differences between query 2, 5 and query 1, 3, and 4. We thought that this was because training distribution was matter. Yeah. So we calculated ELMD, which is inspired by Earth mover distance-based metric in the discrete space. Here, ELMD means that distance means a distance from changing composition A into composition B in the chemistry field. So we calculated ELMD between DP compositions in training setup machine learning model and generated DPs here. And we found that for query 2 and query 5, ELMD was high, and query 1, 3, and 4, ELMD value was lower. And also for the prediction result, query 2 and 5, DP generated by query 2 and 5 showed bad performance in CRAMNet, and query 1, 3, and 4, they did good in the CRAMNet prediction. So yeah, as a result, we could conclude that only for in-distribution, machine learning-based text gradient was helpful. So careful use of machine learning-based feedback is required, considering training data distribution. So conclusion of topic 2 was that we constructed a multi-agent text gradient-based framework for conditional DP generation that integrates these gradients. And for the domain knowledge from text gradient, integrating domain knowledge was helpful for stability and DP composition, and machine learning model-based text gradient was partially helpful or partially detrimental. ML-based text gradient provides reliable guidance within ID, but not for OD. So careful consideration for depicting, choosing machine learning model is very important for this problem. So this is concluding remark for these works. We need to consider data distribution, and we need to use appropriate physics or knowledge-based guidance. And also we can use hybrid use of weight tuning and multi-agentic large language model strategy, considering trade-off between time and accuracy. These approaches can enhance performance for such multi-agentic systems. And this is the review paper I wrote, saying that we need to consider problem and data characteristic for deep learning based inverse design. I think we need to, and I hope to expand this framework into the LLM-based multi-agentic system in future. I want to especially thanks to my advisor and team members who have worked together, and I want to thank to funding institution, and thank you again. And these are the paper depicting details of this research work, and thank you for listening again.
Thank you, Junhyung, for presenting your work. Do we have more questions for the speaker?
Hi, Lee. That was a great talk. I'm Rutvik. I'm a PhD student at the Crunch Group. So I had a couple of questions regarding the second half of your presentation where you were talking about the generative models.
Yeah.
So for the generative models, what kind of models are you using for the generator? Are you using VAEs or are you also exploring diffusion models for the same?
For the second topic.
Yeah, for the second topic. So you say that you have a generator which generates the composition.
Yeah.
So what kind of generator models do you use there?
The generative model I have used was just open large language model. It was all three mini. Yeah.
I see. Okay. And then when you say that you provide some kind of prior using the LLMs, right? So you say that in order to push these generative models to perform well in the out of distribution regime, you try to provide them additional information using LLMs.
Yeah, right.
Right. So while using the LLMs, do you also augment them with additional information using RAG data or using some specific knowledge graphs that you build specifically for the problems that you're trying to target, or are you directly using the LLMs as it is?
Yeah, that might be a really great idea. I think that is very good future work direction. Yeah.
Okay. Right.
Yeah.
Right. And one final question. So I think at the end you were talking about the Earth mover distance, where you were talking about how having a higher Earth mover distance is essentially meaning that your generative model is moving out of the training distribution regime to predict or discover new compositions. So can we kind of impose that as an additional constraint to the loss function, where you're forcing the model to predict compositions that have larger Earth mover distance? Because from what I understand, you're trying to push the boundaries and get these models to predict new compositions which have larger Earth mover distance. Does that make sense?
Oh, thank you for a great insight. Surprisingly, I am preparing those kind of future works. Yeah.
Sure. But is that a viable option, or or do you think there are some consequences with that, or maybe if there are some pitfalls with these approaches?
Let me see. Did I prepare the slide? Let me.
Sorry to interrupt, but we are not seeing any screen right now, Junhyung.
Oh, really? Okay. I'll share. Yeah. Sorry for delay and technical issues. Yeah, this slide. Yeah. Here, in this work, we something like assume that there will be optima in the ID, but if we have optima in the out of the domain, people will actively learn with their data with fine tuning like this way. Yeah. So the first matter we need to do is that knowing where is our optima, but that's not possible, I think. So I think there will be two track of research that finding optima outside of the scene domain using fine tuning or other active learning based method. And one other thing will be people will do exploring ID well problem, supposing that there will be optima in the ID domain.
Right.
Yeah.
Okay, got it. And about the second thing, I think the Earth mover distance, something that you're presenting almost at the end of your talk.
I'm sorry.
The Earth mover distance that you were presenting almost at the end of your talk, where like I think you show like for query 2 and query 5, you have larger earth mover distance, which means that the model is able to like predict somewhere like out of the training regime.
Yeah. Right.
Right. So here like would it be like a possible approach to like explore that you have this earth mover distance that you want to maximize when you are predicting the compositions, like have this as an additional constraint when the generator is trying to predict a new composition.
Yeah, that is exactly what I want to in the future work. I want to add this as a loss function or fitness function to the active learning objective function. Yeah.
Right. Got it.
Yeah.
Okay, thank you. Yeah, great talk.
Yeah, thank you for your nice discussion and nice insight.
Right, Zhang, maybe I have one question.
Yeah.
Can you go back to the previous slide that you were showing about where you had like this star solution? And
Yeah.
The one that you showed.
Yeah, this solution.
Yeah, this one. In this case, it's like this, like your guess that the star solution will be outside of the domain, or it's like somehow like people actually constrain that. And the reason why I'm asking is because I thought that when you do, let's say, training, and you usually do is like, let's say, you do this grid, and then you have observations here, observations here, observations here.
Yeah.
And when you end up finding is not something that is here, but maybe something that it's around here, that it's just something that you didn't consider, but it's still inside distribution. And and this comes because if you force the model to go outside of this, aren't you like a bit more susceptible to things like hallucinations or these things that the agent can just say something that doesn't much make sense?
Yeah, I think so. Yeah.
So in that case, why would it be advantageous to go outside of this domain? How do you know that going outside the domain will not lead to hallucinations? That's maybe the question.
Actually, there have been some works have fine-tuned large language models, assuming that there will be an optima outside the scene domain. But this slide mentioned that. Let me see. If I turn the PowerPoint. Okay, I will explain here. Yeah.
Let me remove what I wrote.
Yeah, it's okay. Your question is yeah.
The question is like, I understand what you're saying, that maybe you want to get this star solution by going out of the sync domain, but then what it brings up is like, okay, that may make sense in some cases, but how do you avoid like making your model more susceptible to hallucinations?
More susceptible hallucination. Going out of scene domain, there will be hallucination, right? So I prepared some research work, have done this kind of strategy. They additionally calculated their own data and accumulated their own data to fine-tune this model. But one of the paper I have read that deep learning model has no extrapolation capability, but for the near scene domain, very nearly scene domain, they have some kind of very slight extrapolation capability for those ones. So for large language model, this will be surely the hallucination region. Yeah, very susceptible to hallucination, right?
Yes, but then it doesn't make because one of the reasons why people is a bit worry about LLMs is because they don't trust it that much, because they say a lot of things that sounds right, but they are not. So if you give them the freedom to give you these things, how are you making sure? Do you have any like control or like some way to make sure that the solution that they are giving you makes sense?
So your question is that even if we explore ID or OD, LLM can hallucinate. So will people believe that solution?
Yeah, how do you verify that that's a valid solution?
Actually, that is very difficult question. For our framework, we validated the proposed solution by a large language model using DFT calculation. However, in the most of case, this kind of calculation might not be possible.
Sorry to interrupt, but as you were suggesting, like you had some other loss terms also, right? You were having some other constraints which were coming from the physics-based constraints or LLM-based constraints. So imposing those kind of constraints, I'm assuming may help you to like expand the exploration zone a little more, but however also prevent the LLM from hallucinating a lot. I'm just hypothesizing. I'm not sure.
There was the hypothesis, but there will be innate hallucination capability of this generator, even if we have condition like this way. So
right, yeah.
Yeah, right. We have alleviated that kind of hallucination, but we could not prevent perfectly that hallucination. So there might be great future work, but at now stage, I cannot guarantee that.
I'll go ahead with your question.
Yeah, Joel, thanks for your work. Thanks for your talk. It's really cool. Just one question about the second part of your work. I really love the idea of thinking of these directions as like the gradients to change.
Oh, thank you so much.
Yeah, I think that's a cool idea. But I just wanted to ask, if we, when we do optimization using gradients in the traditional sense, we get all kinds of problems. For example, it might take very long for the gradients to converge to the minimum, and you might not find a global minimum. You can get trapped in a local minimum or a saddle range.
Right.
What would be the analogy of these kinds of problems in your work, and how can you address them? For example, how long does it take for these kind of LLM-based text gradients to converge, and how can you make it converging in the right direction that actually gives you a better solution?
Oh, thank you for your really great question. Let me share one more slide here.
Jingjing, I think we are not. Yeah, that's good. Coming back.
Yeah. Okay, back here. This is the trajectory of the LLM generator, the composition LLM generator have generated. Actually, adding case 2 is the only with LLM pre-trained model, and case 3 is kind of generating with domain knowledge here. And we have found that with the domain knowledge, the anion is converged to F, right? So this is I think this is kind of local optima by this domain knowledge. So additional domain knowledge or additional stimuli into the multi-agent system will solve this kind of local optima problem. But there might be great future research work, I think. But
Yeah. I think this is cool. There are many analogies that we can draw between LLM doing optimizing or something and optimization in the traditional sense. I think it will be an interesting topic to study.
Yeah, I think so. And my future work, we would like that. So I want to apply this optimization strategy into various kind of problem, multi-objective, or as you mentioned, finding global optima other than local optima, or transfer learning, any kind of,
Yeah. Sounds good.
Thank you.
Thank you.
Thank you.
Do we have any other questions for the speaker?
Varun, do you have any other questions, Varun?
No, not really. Thank you.
Thank you.
If not, I would like to thank Jingjing again for staying up so late to present this work and presenting it to the Crunch seminar. Thank you. And I'd like to thank both speakers and have a nice weekend. And I'd like to close this week's Crunch seminar with that. Thank you all.
Thank you.
Thank
Bye-bye.
you. Thank you.